morning and welcome to this two-day program of mathematics titled History, Aspects and Prospects of Mathematics in India. This is a program sponsored by the three academies, the three scientific academies, and it's being hosted by the Institute of Mathematical Sciences here. I happen to be the convener. My name is Raghavan, and if there is you can contact me for any organizational problems or necessities. Okay? And it is my pleasure to ask Professor Balasubramanian, Director Math Science, to say a few words of welcome.
Yeah, of course, let me at the outset welcome all of you for this today's conference on history, aspects and prospects. Let me thank the let me thank you. Let me thank the three academies for having given this opportunity. And let me thank Professor Raghavan, who has taken the initiative to run this here. And as you do understand, one of the aims of this conference, this workshop, is essentially for the young students here to listen to the experts who have come here to give the lectures on the various aspects, and besides, to interact with them, to know who are the great mathematicians in India. For example, S.G.Dani is here, and he is one of the top mathematicians, and this is an opportunity for all of you to meet S.G.Dani and talk to him. And further, it's not even clear to me for how many of you this will be your first visit to this institute. Probably you might not have even heard about this particular institute even earlier, and therefore should know that such an institute exists and try to understand what is going on in this institute. In this connection, I would say that feel free to meet any of our faculty members, either in mathematics or in physics or in computer science, whatever subject you are interested, and talk to them and know about their interest and about your interest and whether your interest to deal with that. And more than that, we have a library. I can sort of probably say that sort of a well-equipped library, and which is open for anybody who wants to use it during the office hours of the working day. You can now also take this opportunity to go around the library to see what sort of books and journals the library has, so that if you live on all the space and you are free, and it's open on Saturdays too, and so that you will be able to use this library. And therefore this will give you an opportunity to know about this particular research institute, an opportunity to know the experts who have come here to give lectures from, an opportunity to know what is the mathematical scenario in India today, either in terms of research or in terms of the applications of mathematics, or to see what are the departments that would be needing the mathematician in their payroll for their purposes, and so on. And I hope you would all utilize this opportunity well. And thank you once again for having me.
One of the ideas behind this program is that students have an opportunity to meet and interact and talk to not just the speakers, but also other eminent people who are not speaking, and some of these are chairpersons, some of these are invitees. I extend a special welcome to Professor Sridharan, who is here, and it's my pleasure to welcome another of these eminent people, Professor M.D. Srinivas, to chair the session in which Professor Dani is going to speak. Professor Srinivas.
Friends, it's a great honor pleasure to introduce the speaker of the morning, Professor S.G.Dani, one of the eminent mathematicians of our country. He was a student of the Tata Institute, became a faculty there, is a professor there. He has done eminent work recognized all over the world in the areas of Lie groups and ergodic theory, about which I am not competent to comment. But he has also been concerned with larger issues of development of mathematics in India. He has been a member of the National Board for Higher Mathematics and has later become its chairman. Recently, he has taken over a new responsibility as the president of the Indian Society for History of Mathematics. I don't know, many of you would not have heard of the name of Professor R.C. Gupta, one of the great historians of mathematics from India, who recently, in the last International Congress of Mathematicians, received a special prize for his lifetime work on history of mathematics. He started this Ganita Bharati Association and brought out one of the few world-class journals which are published from India, but which is devoted to history of mathematics and which has run uninterrupted from the 70s. Recently, Professor Gupta has become old, and Professor Dani has taken the onerous responsibility of continuing this journal, which he is doing admirably already. One issue has come and a couple of issues are in the anvil. Professor Dani has also had an abiding interest in history of mathematics. He has looked deeply into the ancient texts of Indian geometry, shulba sutras, and had written articles with a lot of insights concerning the development of geometry in India. I'm very glad that this program on history, aspects, and prospects has chosen to start with an overview of history of Indian mathematics. Unfortunately, not many of us would be taught any history of mathematics. Not many mathematicians or even others, scholars, happen to know much about history of mathematics. So it's high time we give it its due importance in our intellectual pursuits. Today happens to be 100 years since the first published work on a textbook of Indian mathematics, that was the Ganita Sara Sangraha of Mahavira, which was the first work which was exclusively devoted to mathematics in India. This was written in 9th century. It was published exactly 100 years ago. It was the first such work to be published by Professor M. Rangacharya in this city of Madras. Earlier than that, only Aryabhatiya was published. It has only about 30 cryptic verses on mathematics. It was published in late 19th century by Bruce Kern in Leiden. So when Ramanujan was training himself in mathematics, he neither had access to any of the sources of the tradition of mathematics from which he came, or to experts who could tell him about it in the colleges or universities. Anyway, recently, just to highlight the importance of knowing the history of mathematics, I just want to read a quotation from a very brilliant review by David Mumford of a very important book on history of mathematics in India by Kim Flofker. Mumford's review appears in the March 2010 issue of the Notices of the AMS. Mumford starts with this rhetorical question. Did you know that Vedic priests were using the so-called Pythagorean theorem to construct their fire altars in 800 BCE? That the differential equation for the sine function in finite difference form was described by Indian mathematician astronomers in the 5th century CE, and that Gregory's series, under quotation, for pi by 4 equal to 1 minus 1/3 plus 1/5, etc., was proven using the power series for arc tangent and with ingenious summation methods used to accurately compute pi in southwest India, that is Kerala, in the 14th century. If any of this surprises you, Professor's book is for you. I'm sure it surprises most of you, and Professor Dani will cover some of this ground during the, I hope, the course of his talk. And now, there's one thing that we need to know, that these discoveries were there, etc. But it's much more important to have what is called the long time perspective of the development of mathematics when we take off from our position either as students, as researchers of mathematics, and go up and survey how this great intellectual endeavor of mankind has moved. And here Mumford points out, it's high time that the full story of Indian mathematics from Vedic times through 1600 became generally known. I am not minimizing the genius of the Greeks and their wonderful invention of pure mathematics, but other peoples have been doing math in different ways, and they have often attained the same goals independently. Rigorous mathematics in the Greek style should not be seen as the only way to gain mathematical knowledge. In India, where concrete applications were never far from theory, justifications were more informal and mostly verbal rather than written. One should also recall that European Enlightenment, that's the invention of calculus by Newton, Leibniz, Descartes, and others, was an orgy of correct and important but semi-rigorous math in which the Greek ideals were forgotten. The recent episodes with deep mathematics flowing from quantum field theory and string theory teach us the same lesson, that the muse of mathematics can be wooed in many different ways and her secrets teased out of her. In another context, Professor Mumford had said, the book of mathematics can be read in many different orders. And so they were in India, and read this book, that's Plofker's book. So there is indeed a, Mumford is of course addressing the international community of mathematicians, but there is much more reason for us Indians to know the details of the development of mathematics in our own tradition. And I'm very glad that this meeting done in the mathematics year has indeed started with this very important lecture on history, and it's being given by one of our leading experts. It's a pleasure to welcome Professor Dani to address.
Good morning, everyone. It's a great pleasure for me to be here to be talking to you on the subject. I begin by thanking the academies and the organizers in general for arranging this event, and in particular inviting me to give a presentation on history of mathematics, history of ancient Indian and medieval mathematics. I'd also like to thank Professor M.D. Srinivas for the kind introduction. It's actually an honor for me to be to have him as chairman of the talk. When we think of ancient Indian contributions, generally there are two perspectives. One is that, oh, the Indians didn't know anything, they contributed zero and that was all. So the contribution of Indians is 0 and 0. There is another perspective that India was the fountainhead of all knowledge and everything comes from India, and the rest of the world is simply taking it in various ways, perhaps sometimes stealing it. Well, as it happens in many instances, both these perspectives are quite wrong. Including the general idea that zero came from India itself needs to be understood in a much more nuanced way rather than simply thinking of that as the origin. On the other hand, of course, the idea that everything came from here is also quite wrong. Many cultures in the world, of Greeks, of course, everyone knows. Then the Chinese have made had made a lot of progress. Apart from this part of the world, the Mayans had a lot of mathematics. Then at a somewhat later stage, compared to these ancient cultures, the Arabs made very important contributions to mathematics. So mathematics, and in a broader sense, broader way, science has not been preserve of any culture. I mean, at various times, various cultures have contributed. There have been ups and downs, and it has been the same story with us, with our culture. At some times, we have done very well, contributed greatly. Other times, they have been mired into various problems. Sometimes things were done, but could not get disseminated, could not get absorbed in the social life, and whole kind of rigmarole that takes place in the development in the process of history. Now, so when we look at the subject, the idea is not to prove this point or that point, but the idea is simply to be curious about how things happen. It's not who was doing better, who is borrowed from whom, etc. is an important aspect, but the main point of the study of history of mathematics is to be curious about how our own subject developed, not just in India, but everywhere around the world. Now, the reason why I am talking about India, or why is both because one would of course like to start from home in some sense, and secondly, that is the area in which we have better opportunities. I mean, so many of us are exposed to the ethos here. We know, I don't know about how many one can say that, but we have some smattering of Sanskrit. One can learn the language through our languages in a simpler way than would apply to the people from other parts of the world. So, with these benefits, it certainly more greater responsibility to do the needful in terms of understanding what India has contributed to the process of development of mathematics. And it's at least this has been my perspective for this study, and I do hope you inculcate or imbibe the kind of approach, rather than being motivated by objectives which are somewhat in opposition to a scholarly approach to knowledge. With that, I'll sort of close my introduction. I should really be thankful to Professor Srinivas also for giving you many details and perspectives with regard to development of, with regard to in terms of placing the subject in context. He already mentioned to you about the Shulba Sutras from the Vedic period. There are also various other traditions which we will have occasion to look at, and then he also came back and mentioned to you about the current time, about the Indian Society for History of Mathematics, with which I am associated, and the Ganita Bharati, which was started, as he mentioned, by Professor R.C. Gupta, one of our eminent contributors in history of mathematics. I was surprised that he has an incredible number of more than 500 articles in the subject, and looking at his work itself is a big task project by itself. Should like to mention that the Indian Society for History of Mathematics has a website, and one of the things that we have done there is to give access to some of the papers of Professor Gupta, and you please do visit that and take benefit of that. Now, on the subject of ancient Indian mathematics as a whole, I wrote an article a few months ago. I do not know how many of you would have seen that. This appeared in the 26th December issue of the Hindu, which had a special pull-out on the Ramanujan 125 years and so on. And that article was also recently reprinted in Resonance. So, for a broader view of the structure, or how one would sort of get a bird's view, that article would probably be helpful. So, in case you have not seen that, I would recommend it to have a look at it. Of course, there are many other sources, but in terms of a quick thing, I thought since I have written it, there is some point in my mentioning that. So, and another reason for mentioning that is that in some way I have a feeling that that article inspired this event in some sense. So, and then in the context of that, it was planned to have this session and a talk on that. For me, there are two possibilities before me, sort of go just along that article, but I felt firstly that it's too broad a subject to handle in a lecture rather than an article of the kind that is presented there. And secondly, since all of you are already involved with mathematics, unlike the prospective reader I had in mind for the Hindu article, I thought I could go a little deeper into the mathematics itself rather than giving only a bird's eye view. So, which is why I chose this topic of trigonometry in ancient and medieval India. Okay. So, in a broad sense, as you would guess, you would vaguely define, trigonometry is the study of triangles in terms of relationships between the sides, angles and angles of a triangle. Now, this involves also the circle, because the angle parameterizes the circle, and another way of looking at it is the relation between the chords and the arc around that. So, in terms of the accordingly, in terms of the development of ideas, will not restrict only to the strict notion of the functions that we now identify trigonometry with, but let us take a broader view. And in this respect, it will be and to put it in the Indian perspective, we will have these four sort of broad themes or broad periods in mind, or broad traditions in mind. One is the Shulva Sutra period, second is the Jaina tradition, then the astronomy tradition. This is called the Siddhanta tradition or the astronomy tradition. Actually, much of the trigonometry that I will talk about or actually concerns the subject of trigonometry will correspond to the astronomy tradition, and later we will talk about Kerala School of Mathematics, which took the subject to a greater height, and we will say more when we come to the topic. So, before going to the mathematics itself, let me give a broad outline of these four traditions, or what they consist about of, I mean, how one should think about it, etc. Now, to summarize briefly the Shulva Sutra aspect to Shulva Sutra topic. So, there are four major Shulva Sutras with mathematical significance. Now, Shulva Sutra is okay, and now these main ones that we will talk about are Baudhayana, Manava, Apastamba and Katyayana. There are many more Shulva Sutras, because as you know, the Vedic community was a very heterogeneous community, and each community had its own version of the Shulba Sutra, and of course, they're not independent. They all borrowed from each other, but in some ways it would be their own Shulba Sutra. So accordingly, the number of Shulba Sutras would have been very large, but those of mathematical significance that have come down to us are essentially these four. There are versions of these which I'll not go into the technicality here, etc. Okay, Baudhayana, from among these, the Baudhayana is the earliest, and it's generally assigned the period 800 to 500 BCE. BCE is before Common Era, that's the acronym that's currently used in the subject. Katyayana is the latest, which is supposed to be from the period 300 to 100 BCE. Now, Shulba Sutras were compositions in aid of performing yajnas. So, you know, with the Vedic culture is associated the idea of yajna performed with various objectives, and it was the main feature of the interrelationship between man and the divine. There was the yajna, unlike the pujas that we have today. And when the importance of the yajnas was not there any longer, the Shulba Sutras also went into oblivion. But when the yajnas were performed, they were actually very elaborate affair than you might imagine from just looking at today's yajnas. Many of them involved huge platforms which would go extend up to 100 feet, and they had these fire altars which would extend in various different shapes, like birds or turtles and wheel and a variety of other things which would depended on the objective of the yajna. And the sizes of these could typically be 15 feet across, and I mean the height of the bird would be 15 feet, breadth would be along with stretched wings would be about something similar, 15 feet, etc. So there were very elaborate figures both in terms of size, I mean in terms of shape, and this in terms of size they were quite large. And one of the main aspects of constructions of these is to describe how these are to be constructed with small tiles. The tiles would be of the size of square or triangular tiles, which would be moderate sizes, about 1 foot to 1.5 foot. So and here I have mentioned some of the shapes: falcons, other birds, tortoise, water trows, and they were described. Construction was described in terms of standard small size shapes. And apart from these constructions, what is more important from our point of view, from current mathematical interest, is that they involved they gave descriptions, I mean describe various geometric principles as well as various basic geometric constructions. I will come. Okay, let me go to the next thing that I mentioned. The Jainas, well, quite connected with the Hindu culture, but separate in various ways, as you would have studied in your history, and I will not go to deep social aspects of the division, etc. But they also contributed greatly to the mathematical development in over the centuries. Mahavira, one of the names that was mentioned, is one of the major Jain figures, which I'll come to later. Now, Surya Prajnapti, just to give the sense of the time frame, Surya Prajnapti, which is one of the ancient Jain works, is believed to be from the 5th century BCE. At this point, maybe I should emphasize that many of these dates in the Indian context, both with regard to the Vedic period as well as Jaina, are more arrived at through complicated mechanisms, and they are not necessarily very dependable as dates. Surya Prajnapti, and then from the 5th century BCE, the Tattvartha Adhigama Sutra Bhashya. This is a philosophical work associated with Uma Swati, who there are two possible periods for that for him. According to the Shvetambara tradition, he is supposed to have been from around 150 BCE, while according to the Digambara tradition, he is from the 2nd century. Now, unlike the Vedic people, the Jainas were, of course, they were against rituals. They were not involved, did not practice rituals, but their motivation for mathematics came from the contemplation of the cosmos. They had very elaborate models for the cosmos as concentric rings of huge, increasingly double sizes, etc. Now, and that we'll see has led to some geometry, and I'll say a little bit about triangles, etc., which is why I have included this in the talk on trigonometry. Now, I mentioned the early part, namely the 5th century to the 2nd century, or maybe even the 1st century CE. After that, there seems to have been a lull for a long period. There is no significant activity in the early centuries of the Common Era, but after that there is a major revival from around the 9th century. From around the 8th century, Veerasena is one of the important figures from the 8th century. Mahavira Acharya, whose Ganita Sara Sangraha was mentioned by Professor Srinivas. Then Sridhara is also Sridhara is known for this solution of the quadratic equation. We'll not go to that later. Nemi Chandra is another well-known figure. Then Takkura Feru is another of the Jaina contributors, and by this time, the 14th century, the sultanates, the sultanates had set in, were in place, and Takkura Feru was in fact a treasurer of at the Delhi Sultanate. Okay, we'll come to the Siddhanta tradition. This is actually the main theme, school of contributors. In the early centuries of the Common Era, interest developed in India in astronomy and astrology. Notice that the earlier two themes that I spoke about, neither the Shulba Sutra nor the Jainas were involved with astronomy or astrology through astronomy in any case. And associated with the interest in astronomy and astrology, there was also development of mathematics. The early works have a lot of commonality with the Babylonian and Greek astronomy, and also various indicators about the names and so on, which I will not go into. There's something called the Romaka Siddhanta and so on, which suggest influence from abroad, from foreign, more likely from the Babylonian and early Greek astronomy. The later Greek astronomy doesn't seem to have percolated to India. The Siddhanta astronomy, or the Siddhanta tradition, or the astronomy tradition, was the dominant one that was to sort of be seen in India until from 5th to 12th centuries. Now, Aryabhatta, who was already mentioned, is often considered the founder of this tradition. The tradition itself did not start with Aryabhatta as such. Aryabhatta, in fact, is in a sense, Aryabhatta is like Euclid to the Greek tradition. Aryabhatta to the Indian tradition is like Euclid to the Greek tradition. He was summarizing, he was sort of putting together some of the things that were known, and in a nutshell, as was mentioned, it's a very short manuscript. There are only 33 stanzas on mathematics related part in all, and 121 in all, including astronomy and so on, including also there are it would also have stanzas about defining numbers, and also obeisance to the deities and so on. So altogether it's only 121 stanzas. Now the tradition continued more or less continuously. One of the main features of the development of mathematics in India is that one sees a certain continuity, though very feeble. The in each century we see some one or other prominent names. Aryabhata, then Varaha Mihira is from the 6th century. The first Bhaskara. Bhaskaras, there have been 2, so there, and for want of any other better identification, I think they have usually been called Bhaskara 1 and Bhaskara 2, though of course it's not like the European dynasties which say they were Charles 1 or Charles 2. It's just a convenience for of names. Then there is Brahmagupta, Govinda Swami, Shankara Narayana, Manjula, Aryabhata 2. Again the same principle, the first Aryabhata, then the second Aryabhata. Then there is Sripati, Brahmadeva. Bhaskara second is I think lot better known, probably because by his time I think there is a much greater dissemination of knowledge, or at least he contributed to that. Though of course this needs to be kind of looked in a much broader context and perspective. He has a reputation as a good teacher, and the book Leelavati is sort of known to everybody. Leelavati is generally believed to be named after his daughter, and there's a story of her wedding having got misfired in some on account of the a pearl from her necklace having fallen into the water clock, etc. So this probably the story is not entirely based on evidence, but more of a legend. But anyway, the book is Leelavati actually means, as you would know, playful, and the book is a playful presentation of arithmetic, and that could be another reason for the title of the. Anyway, that's an aside. There are also later names: Narayan Pandita, Ganesha, Kamalakara, and some of these names will come across once again later. And the fourth tradition I would like to introduce to you is the Kerala School of Mathematics, and I do hope and believe that many of you would have heard of this tradition by now and would have some familiarity, some understanding of what it is. The tradition actually pertains, as you would see in the screen, to a school which flourished in Kerala from about late 14th century to the early part of the 17th century. But after that, it seems to have been just forgotten or lost, until in 1830, Charles Wyche, around in 1830s, Charles Wyche was an English civil servant with the East India Company. He brought to light these mathematics from this school from Kerala. So there's there's an interesting article by K. Ramasubramanian, one of the collaborators of Professor Srinivas, which will be coming up in the next issue of the Ganita Bharati, which goes into some detail about how how Charles Wyche studied these things, and the period around that time there's an initial sense of disbelief that the natives, the Indians, could have some of the series and other things that we'll discuss a little later, and there was a sense of disbelief that it could have been discovered independently or before Newton and the European workers, and some of that is discussed in an article of Ramasubramanian. I just wanted to mention that. The school originated with Madhava of Sangamagrama. We do not, there are no extant works of Madhava in mathematics. There are some works in astronomy exist, but his work, Madhava's ideas and work, has been described in the later by his successors. And By a school, what you mean here is that there is a continuity of teacher, student, and then student, the next generation having more students, etc. That continued for 200 years, over 200 years. That is what that's the sense in which we talk of the Kerala School of Mathematics. Apart from Madhava, Nilakantha Somayaji is one of the leading personalities in the area. From the Kerala school, and his book Tantra Sangraha has recently been published. Again, Professor Srinivas and his collaborators are responsibly involved in that. Then Yukti Deepika and Kriya Kramakari by Shankara Variyar, and Parameswara's commentary on Lilavati. Then Ganita Yukti Bhasha of Jeshtadeva are some of the important works from the Kerala school. Now, one speciality of this Ganita Yukti Bhasha of Jeshtadeva is it's in Malayalam, unlike the earlier works which are in Sanskrit. Sanskrit used to be the equivalent of what English is today in India until 15th, 16th, or even later centuries. A lot of work was of common interest was generally written in Sanskrit, even though the person may be more conversant with his own. A person may be Marathi speaking or Kannada speaking, etc. So the books were tended to be written in Sanskrit. But in the Kerala school, pretty early, there seems to have been a transition to writing in Malayalam, and this is part of this could have been partly influenced by the interest of the Jesuits, who probably were more comfortable with Malayalam than Sanskrit. Anyway, many of these are asides. I will not. We'll go to the general mathematical contents. Now, you'd all realize that one basic principle involved in trigonometry is the Pythagorean theorem. That if you take a right angle triangle, then the square of the square over the hypotenuse equals the squares over the two sides. The Pythagoras this principle, which is foundational to trigonometry, was well known in the Shulba Sutras, as Professor Srinivas already mentioned to you, as well as in the Jaina tradition. All the 4 Shulba Sutras that I mentioned contain explicit statements of the Pythagoras principle. It may be clarified that there are no proofs given in any of these texts. There is no discussion of proofs, because the way they described their mathematics, they passed on their mathematics, typically consisted of disseminating the statements. The proofs were probably either described only on certain contexts and were never part of the record. The Shulba Sutras, one special feature that I would like to mention in this context is the Shulba Sutras. They use the converse of the Pythagorean principle to construct perpendiculars to given lines. Now, if, very often, typically you have the issue of you are given a line and a point, and then you want a perpendicular to be drawn to the line at the given point. Now, I don't need to recall to you how we do today. We take 2 equidistant points and then cut arcs and then draw the perpendicular, draw the point where the intersecting circular segments on either side cross. And so, the principle is that if you have 2 intersecting circles, then the line joining the centers and the line joining the points of intersection, they are mutually perpendicular. This idea, this was of course known, and this is also used in the Shulba Sutras, but more commonly they used the converse of the Pythagoras theorem to construct perpendiculars. So, how does one use the converse of the Pythagoras theorem? Namely, so first of all, converse of the Pythagoras theorem means that if you have a triangle in which the square on one side is equals the square of sum of squares of the other 2 sides, then the angle opposite to the bigger square is actually a right angle. right. So, what you would do is to take a rope, then let us say for example, you make marks on that which are in the proportion 3 and 5 and put it take 2 poles at distance 4 and stretch this thread with the mark on the in the proportion 5 to 3. So, in all this you will have a triangle in this way which has sides in the proportion 3, 4 and 5. So, this way you get the angle which is a right angle. I don't think I suppose it should be clear, and if you have not completely understood it, do go back to it and see how it should work. So, the idea is that, so the same thing can be done with any triple like any other Pythagorean triple like 5, 12, 13. So, you have 13 plus 5 is 18. So, you take a string of length 18, mark it dividing 13 and 5. Now, take 2 poles at a distance 12 and then tie the ends of this 18 length string and stretch it with the mark in the proportion of 13 and 5. So, yeah, so that will again give you a right angle triangle. Okay, there's again a bit of a digression there. Let us go back. Yeah, I have described what is said here. Now, the Pythagorean principle is not found stated explicitly in the Jaina literature, but from the overall context it is clear that they they definitely knew the Pythagorean principle, and in fact, some of the formulae that we will discuss would have been obtained by extrapolation of the understanding of the Pythagorean theorem. Let us go into the subject per se. So, now, to be able to talk of trigonometry, there has to be a notion of angle. So, this is a sense of how you would measure angles. Now, this is first of all, this is what is missing in the earlier two streams. There are no measurements of angles introduced either in the Shulba Sutras or the Jaina tradition. There are no explicitly formulated notion of the right angle, even though it was involved in various constructions of squares, rectangles, etc. So, when the Shulba Sutras talk of the figures, they are all in terms of fully constructed figures like rectangles, trapezia, etc. So, there is no name for the right angle as such. So, I have elsewhere sort of argued, described to how to an extent they reached the idea of identifying the right angle, but never actually got down to use that. So, anyway, I will not dwell more on that. So, the point to be made is that people had still not started measuring the angles in the way we do. So, thus there is no trigonometry in the strict sense of the term. So, let me make it very clear. I am not making by including the names Shulba Sutras or the Jaina tradition, I am not making any case that there was a trigonometry there. It is just to put it in the background. Thus, there is no trigonometry in the strict sense of the term. However, some understanding along the lines is seen to be implicit. And I just want to, from the Shulba Sutras, I just want to give one example. For example, Mano Shulba Sutra states that the side of the largest square inscribed in a circle is 3 parts less in 10 than the diameter. So, it tells you that if you take a circle and take the largest square inscribed in that, you can see that it has to be the one which makes 45 degrees angle in the way that we understand. And the length of the side of that square is said to be described to be 7/10. So, this will be the value of 1 over root 2, and you can see that it's fairly close to this value of 1 over root 2. The Jainas had more elaborate formulae for chords of the circle, which we shall see next. Yeah, consider a chord in a circle. In a circle which should be with diameter d, I think I should draw a diagram. So this is a big circle, and there is a chord here, and yeah. So the diameter of this circle is d. Somewhere here, it's the this is diameter. This is the chord, and this is it's called the height, and this is a. The figure, I'm afraid, is not very good, but it's a circle, and basically I'm interested in this arc segment cut out by the chord. Okay. So C is the length of the chord, A is the length of the smaller arc. The chord cuts the circle into two arcs. I am taking the smaller arc. H is the length of the arrow. So you can see that this in the bow and arrow shape. The length of the arrow is only from the chord to the segment of the circle. H, the Jainas had the following formulae relating these quantities. C square equals 4 times h into d minus h. All the quantities are clear to you. C square equals 4 times h time into d minus h, and C square, this the second one is the one which relates the arc to the chord. C square equals a square minus 6 times h square. Okay, these formulas are believed to go back to the Jaina canonical works, which belong to the period 500 to 300 BCE, and are also repeated in the subsequent works such as of Umaswati, and later also in Mahavira and Nemi Chandra and so on. The first one, which is a simple exercise which you should which you can work out yourself, can be seen to come from the similarity of. So if I draw this and to the other end, look at this triangle is similar to this triangle. Therefore, this ratio will be same as this ratio, and that's what the formula corresponds to. So okay, now it's the other one which I would like to highlight to you. The first of all, one should notice that the formula is only approximate. It's not an exact relation, so it could not have been derived from anything, but surmised in some, arrived at by some kind of expectation, etc. And the possibility is that, see, if you try to work this out, this is going to be c by 2 squared plus h squared square root, right? That's what this quantity is going to be. And then this they expected somehow to be about 3.5 times 3 by 2 times, so 1.5 times this thing. It's a kind of expectation, and based on that, if you work out, that's what will lead you to the other formula. So this is what I meant by, this sort of has to be based on the Pythagorean principle is already implicit, and there's a certain geometric expectation that has been built into arriving at this formula. Now, so if we now view the lights can be off. If we view arc length as the measure of the angle, so, then we see that here angle, the chord length and the angles are being getting related. So we are sort of beginning. It's a sort of step moving towards the trigonometry of later years in some way. Now, one thing to notice is that if we look at the special case of diameter itself as the chord, then what you the formula was c square equals a square minus 6h square, or equivalently a square equals c square plus 6h square, and if you take chord to be twice the radius and height equal, height will be for the diameter, the height will be r and chord will be 2r. So, you will get a square equals 10 r square, which corresponds to pi being square root of 10. And this was a value of pi adopted by Jains for over a long period, and in fact even longer, much after Aryabhata's more accurate value for pi. I mean, in some ways, of course, that would be simply because it's much simpler of the simpler expression, like we have preference to use 22/7. So, in that way, pi equal to square root of 10 was used over a long period, and so is generally referred to as the Jaina value of pi. And so I have commented that this was a value used for pi, and perhaps the choice of in the formula, I mean, there is a kind of bit of fitting has been done, and that that already takes into account that square root pi square should be 10. The formula is can be seen is it turns out to be correct. I mean, closer to is a for small angles, it's relatively close, and in general it involves an error of about 1%. Let us come now to the Siddhanta tradition. Trigonometry, akin to what we study, appeared in India in the early centuries of CE, as we said. Some of the early major works are Surya Siddhanta, whose author is not known to us. Then Aryabhatiya of Aryabhata and Pancha Siddhantika of Varahamihira are the earliest extant works in this respect. So, they pursued, as we discussed earlier, they pursued similar goals as Greek trigonometry, but the emphasis was different in various ways, and in particular in the course of that they developed the theory of indeterminate equations. So, this is a more algebraic part, but they I mean, since they involved studying periodic motions, such a periodic phenomena of motions of planets, etc., they got into integral solutions of equations, both linear and what are called Varga Prakriti, the square natured equations. We will not go into that, but that is one of the important fallout of the study of trigonometry. Now, one major difference between the Greek trigonometry and the Indian trigonometry was that while the Greek trigonometry based itself on the length of chords, and the arc around that, while actually the Indian trigonometry had is similar, was looking at the half chords, which is what the sine function corresponds to now. So, in fact the sine function, the name sine is a kind of derivative after going through various Arab and European works. So, I will not go into the sequence of how that happened. Also, there seems to be some variation between interpretations, etc. But the name sine comes from the Sanskrit word ja, or sometimes also it has been derived from another word called jiva. But the idea of using the half chord seems to have made a lot of difference as in terms of studying trigonometry, and that started in India. So, this is the picture. The ja is the sine, and koti ja is what we now call cosine, and they also used very often worked out in things in terms of what is the difference of the radius, and so 1 minus cos theta, which is called the utkrama ja. Now, as we know, one of the important things in trigonometry is to have something like the sine tables, to have to know the sines of various corresponding to various angles. The tabulations for sines or the sine or the half chord, they were not with respect to the unit circle as we do today, which is this is something important to keep in mind. and not with respect to the unit circle, but with respect to a circle with a chosen large value of r. So, you think of be a circle of big radius, and then you think you want to tabulate the arc lengths for corresponding to various degrees. And this radius, different astronomers chose different values of r, and the r was the trija, the radius is the trija. Trija corresponds to 3 signs in the zodiac. So, the 3 signs in the zodiac would correspond would then correspond to that chord. Chord will correspond to the diameter, and the corresponding half chord is the trija, which is actually the radius of the. So, but the 3 comes from that it corresponds to 3 signs. As many as 25 values have been noted for r in different books. Varahamihira's Pancha Siddhantika use the value r equal to 120. Brahmagupta used 3270. Now, and to distinguish from the sine function, we shall write the corresponding scaled up function by sine with capital S. Okay. Now, despite the fact that there are numerous choices for r, one choice was more common, and that came from that was common both to Surya Siddhanta and Aryabhatiya, and that was the value 3438. Now, one would wonder why such a peculiar value 3438. What's the big deal of choosing this as the radius? It turns out that this choice is interesting because the circumference of this circle would be 21,601.6. I mean, it will depend on precisely what value of pi that you choose, but it's in that ballpark, and which is close to 21,600, and 21,600, which now is essentially the circumference, is the number of minutes. You divide the circle is divided into 360 degrees, and each degree is divided into 60 minutes, and so on. This is a division that you know already, and so in a circle there are 21,600 minutes, and the radius is such that the circumference has a natural division into 21,600 minutes. So, now if you take r sin theta, then for small angles, you know that sin theta is going to be theta. So, here when you say for this radius, the property will be, if you take the 1 degree, so the sine of 1 degree is going to be like 1 degree, and in this measure it is actually going to be 60, because it is 60 minutes, right. Similarly, so if it the first step in some sense would automatically be set down. So, the sine of 1 degree will be 60, or sine of 1.5 degree will be 90, because the 1.5 degree is 90 minutes. So, because of this choice, you don't have to need to do any further conversion. Okay. And this is the same advantage that this is the same reason for which we now parameterize the circle in terms of the radians. So, the sin theta automatically becomes theta. So, because the angle is measured in radians, theta radians. So, and the similar advantage they enjoyed by choosing the particular figure for the radius. Okay, Aryabhatiya of Aryabhata and Pancha Siddhantika of Varahamihira, they gave sine tables with these radius that I mentioned, and with a step size of 225 minutes. So, it's not 3.45, 3 degrees and 45 minutes. Anyway, 225 minutes is the right. 225 minutes is the step size. So, 225 minutes, then 450 minutes, and so in multiples of 225 minutes, there will be 24 up to 90 degrees. So, that angles are described. So, now in other words, from 0 to 90 degrees, which is what you need to give, the 24 number of 24 parts that have been made. Now, sometimes people tell you that this division, I mean, there is an actual ancient statement that the 96th part of a circle looks like a rod, straight or straight. So, and sometimes people tell you that in the ancient times or Bhaskara, I mean during this period, the circle was itself thought of as being a regular 96 sided polygon, and there is even allusion to saying that since it has to be since iron ball, if you make an iron ball, it has to rest. So that some part has to be, there has to be a certain flatness, and it's of the order of 1 by 96. So there's a certain belief among some people that at some point the circle was thought of as like a 96 sided regular polygon, but that's actually only is a kind of general statement, only to the effect that it's enough to understand, it's enough to divide the circle into 96 parts as far as understanding these things are concerned, because that's small enough that that's the sense in which 96, the 24 was important. The real significance of 24 parts is that while on the one hand it is adequate for applications, it's small enough for the measurements that they were interested in. On the other hand, it was feasible computationally with moderate effort to determine these values. So, up to 24 we could do it relatively easily. We'll go into some of these details of how they worked out. Okay. Now, the sign again the sign tables were not described in terms of each value, but the successive differences. So, here is the statement from Aryabhatiya, which tells you the successive sign differences. The yeah, these figures, these are the successive first sign from 0 to the 225 minutes. So, that is this is 225 itself. Then this next one, it is 224, namely the sign of double this is you have to add 224. Then the next time the difference is 222. 219, etc. Okay, and this is what this thing describes. And here there is a notation involved. The numbers are written. The Makhi means 225. Here actually ma stands for 25, and kha is 2. It's 225. It's the numbers are in the old times were in the reverse order. Okay, and I also copied down for you the table. So though of course it's not part of the main theme. So ka equal to 1, kha is 2, ga is 3, etc. Ma is 25, and then I have not copied down here, but yara, lava, sha up to ha, they were given the values 30, 40, 50, 60 up to 100, and that's with this notation that these are the numbers of the successive differences that turn out to be these numbers. And so, it is not the values of signs themselves that were tabulated, but the successive differences. These tables turn out to be quite accurate. I will not go into precise comparisons. There are two principal methods for by which the tables were computed. One method involves knowing the formula for the sine of half the angle. Now, we know of course, in a natural way the values of sine for 30 degrees, 45 degrees and 60 degrees, and now okay, this formula for corresponding to, of course, they did in terms of this capital sign with capital sign rather than the sin theta, but for our understanding let us look at things in terms of in these terms. So, the formula for sin theta by 2 equal to half of which is same. This is a standard formula that you would know. This was known, and this was known already from the time of the Surya Siddhanta. And okay, so once you know the values for the 30 degrees, 45 degrees and 60 degrees. By halving we get those corresponding to 1, 2, 3, 4, 6 and 20, and by complementing you get 23, 22, 21, 20, 18, and again you use the formula. So, successively you starting with these values and this and the fact that you know the complement, I mean for the complementary, so sin square plus cos square equals 1, that using these two you can compute the 24 terms of the table that you want. That was one method, and another method, a second method is via the formula for a difference, for the difference of successive signs. Now, such a formula is described in the Aryabhatiya. However, it turns out that the wording is cryptic and is open to interpretations in various ways and so on, but nevertheless a formula like this, the delta L plus 1 minus delta n by Sn equal to delta 2 by minus delta 1 by S1, where here Sn is the nth term of the table that you want, and delta n is the difference of the two, that and Sn is the sign at the nth step and delta n is the difference of these two, and then this is the this relation would have been known, and once you know this, then you can compute the sign table. Okay. Now, it is interesting that this is essentially like the differential equation for this sign. So, it is this finite version of the differential equation for this sign. So, that is actually what you would have noticed, that Professor Srinivas read out a quotation from Professor Mumford, and Mumford makes an allusion to the fact of differential equation of the sign having been known, but this is what it is about. The the relation, this relation, something like this relation was known, and so it is okay, and was used in computing the tables. Okay. However, there is also an observation that this would not have been a method by which the entire table was computed, because of the fact that these differences at each stage they would involve a certain error, the error would accumulate, and people have conjectured, some people believe that the actual values were not could not have been computed only, from this table, but perhaps by a combination of the two methods, or yeah. Knowing, I mean, you use the formula for half at various stages, and then use the differences formula in some way. Okay, then here are the values. The comparisons, as I said, are fairly close, but I will not go into that. Okay. Now, apart from the steps, though as I said, up to some point it was always it was in some sense sufficient to have the table at a step size of 225 minutes, as when there are finer things involved, you need to know how to go beyond and say maybe how to get the sign for 1 degree or half a degree, etc. Now, so one way that one would imagine is to use interpolation, and interpolation was indeed used from the very early times to get values of sines between the angles. So, between these step sizes, if you wanted to compute the sine, take the additional segment, think of the proportional distribution of that, what you would call linear interpolation, and get the actual value, get the value of sine for that angle. So, this was also adopted, and this was adopted starting from the Surya Siddhanta, and also this could be done also in the reverse direction, linear interpolation that was done. There is also a more refined form of interpolation which takes into account how rapidly the function is increasing in some sense, and that is seen in Brahmagupta's Khandakadhyaka, and also one of his earlier Dhyana Grahopadesha, but surprisingly it is not found in his main work, the Brahmasputa Siddhanta. Another intriguing thing in the Indian astronomy is this curious formula that goes to first Bhaskara the first, the formula is from around 600 CE. So, here sin theta is given to be this is sine with radius r, 4 times theta times 180 minus theta divided by 40,500 minus theta times 180 minus theta. And this okay. So, in terms of pi, or in terms of our usual sine function, this corresponds to the formula sin theta is approximately 4 theta times pi minus theta, 5 by 4 pi square minus theta times pi minus theta. Okay. So, this formula actually turns out to be very very close, and here is the graphical comparison of the two. So, you can see that this function is the sine function, whereas this function is the ratio of the quadratics. So, in this part you hardly see any difference in the graph. Of course, there is an error of about less than 1%, which you do not see in the graph. So, the point is it is a fairly accurate formula. It may be noticed, however, that the ratio sin theta by theta actually tends to 16 by 5 pi, which is 1.0185 rather than 1. It should actually have for the correct function it should go to 1, but the limit is slightly off, leading to an error for small angles. But when the angle is small, numerically the error would be small anyway with that ratio. So, okay. Now, several modifications of this formula were also propounded by later mathematicians all the way until 16th century. So, in Ganesh Devana's work in 15 and 20, we see the formula where the number in the bottom at the bottom has been modified. It is actually 180 less than the original figure 40,500. So, and apparently Ganesh Devana always used this formula to and took no recourse to the sine tables. So, that computation was always made without the tables with adjustments. There is no indication in the ancient literature how the formula was arrived at. In recent literature, various methods have been proposed by which it may have been arrived at. Basically, since these are, it has to be 0 at 0 and 0 at 180. In some sense, these two factors are to be expected, and what is the adjustment needs can be worked out. I mean, perhaps x was computed by trying to fit various values, but what is interesting is that it works out so well. Here is also a formula from Brahmasputa Siddhanta for the arc length, which is a kind of reversal of Bhaskara's formula. I will not go deeper into that. Similarly, Bhaskara has Bhaskara the second gives a formula for the angle in terms of the circumference. See, here is the circumference, and which is again Bhaskara's formula worked in the reverse direction. Okay, now we need to refine the tables, sine tables, and some further new inputs were needed, and these new inputs came with Bhaskara the second. Bhaskara the second found actual formulae for sine of 18 degrees equal to 1/4 of r times square root of 5 minus 1, and sine of 36 equals 5 minus square root of 5 divided by 5, and then take square root. So, these two formulas actually were described by Bhaskara the second. With these together, and then also the earlier formula for sine theta by 2 was extended to difference of, sine of difference of the two angles is equal to this. And with these two, Bhaskara derives a table for each with a step size of 3 degrees. Okay, Bhaskara describes a procedure to obtain sine table with 30-degree interval. I mean, so sorry, this is 3-degree interval, 3-degree interval along with the following lines. Okay, so together with what we know already, we know sine the sixth. This is 3-degree interval. So sixth is this is 18 degrees, 30 degrees, then 36 degrees is already given. So these the 6th term, 10th term, etc. of the table are now known to us with these two and the standard ones. And then by by halving, you can get these by halving, and using the above formula, you can then get second and hence 28th term of the table. But again, by halving, you get first and the 14th. This is actually described in one of the stanzas in Siddhanta Shiromani. And interestingly, after coming to this, there are still some things are left, and it said the remaining in a similar way is what is concluded. One can actually check that the remaining can be done in a similar way, but the point I am making is that it's this there also it's said in a similar way. Okay, so the point I would like to note here, observe here, is that after knowing some of the terms, you would have thought that you could simply use the formula for sums or different sums and differences, but it doesn't. There he's actually using the formula for half the difference. So and I'll come to this, elaborate on this a little later. What happened? Okay, this, how do I? Then Bhaskara also extended the table to 1 degree by this formula, which is actually some kind of interpolation. We need not say too much about this. Theta, sine of theta plus 1 plus or minus 1 degree is this. So here some kind of formula for this sum seems to be involved, but it's not clear exactly how, whether that was what was used, or some other considerations were used to arrive at that. Now let's ask about the formula for sine itself. Formula for sine of sums. At a later stage in Siddhanta Shiromani, this formula is also described. Sine of theta plus phi equals sine theta cos phi plus cos theta sin phi, and similarly with the minus sign. There are no proofs given, but it is believed that this was kind of it has been suggested the formula for the sums and differences was guessed based on the knowledge of solutions of Diophantine equations. So it was not actually derived geometrically perhaps, but since then they had understood how the solutions of Pell's equation and things like that they work, and one of course notices that if you take the right hand side and then it would satisfy the expected equation about the sine square plus cos square equal to 1, and from that it was perhaps guessed, and which perhaps explains why they didn't use this formula, though it was known, it was not treated with the same degree of confidence. Is a possibility that one may have to keep in mind. Okay, now we come to post Bhaskara period. May I take about 10 minutes? Okay. We now come to the post Bhaskara period. There are various names. Mahendra Suri, Kamalakara are some of the names. The Mahendra Suri's Yantra Raja is notable because by then there seems to have been kind of exchange between the Arabs and Indians. Yantra Raja is based on some of the Arab work. Now, Kamalakara's specialty seems to have been very fascinated with trigonometric computations, and the various formulae are actually worked out. Sin theta, these of course need are based on the formula for sums, etc. And I think Kamalakara tended to give many proofs, so they probably he knew all these things with proof. Sin theta equals sin theta, this is the usual formula that you would know. Sin 4 theta equals 4 times cos cube theta sin theta minus sin cube theta cos theta, and similarly a formula for sin raised to 5 theta. He also notes the formula for theta by 3 and theta by 5. Sin of theta by 3 equals 1/3 sin theta plus 4 by 81 sin cube theta, and similarly for this thing. Now, these are actually not derived by solving the cubic equation that this would involve. What is done is that for sin theta by n, you make a replacement sin theta by n, which is approximately correct for small angles. Then when in this equation, when you replace this term by sin 3 theta by 3 cube. So that's what gives this 4 by 81. And now so then replace 3 theta by say phi. So these two terms will come here, and here we have this phi by 3. So phi by 3 will be sin of phi by 3 will be 1 by 1/3 sin phi by plus 4 by 81 sin cube phi by, yeah. And similarly for the fifth part. Let us now come to the Kerala school. The trigonometry now reached a very dramatic heights with the Kerala school of Madhava. The sine table, though it's still adopted a step size of 225 degrees, 225 minutes, the entries are much more accurate. They are accurate to the 7th decimal point. In this respect, the radius of the reference circle was redefined. So everything was getting finer, more focused. It's the reference circle, instead of 3438 is what we had seen, it was chosen to have radius 3437, then plus 44 by 60 plus 48 by 3600. That's what this notation would stand for. And systematic proofs were written down for various formulae, including for the signs of sums and differences. Now, I have not seen the original, but so Divakaran, who has been has studied these things much more than I have, said that they seem to be quite impressed to have found to be proving the formulae for sums and differences using geometric methods. Make a song and dance of it is what are his words. Ideas akin to modern calculus, such as series expansion, Riemann sums, were developed in the Kerala school. So this is a whole change of game changer ideas already were there. Series expansions, Riemann sums. Series expansions were found for the arctan function, the tan inverse theta function. And in particular, so the pi by 4 could be computed with that. And then the series expansions, the Taylor series expansions for sine and cosine functions, they were arrived at. So the value of pi was determined accurate to 11 decimals, and with a ingenious truncation correction method. I will say a little more about this, but before that, maybe here is Madhava's sine table. So as you see, and was stated, the step size is same as before, 345, 730, etc., which is this is 225 minutes, and the sine now is slightly less than 225. So and here this comes to the finally this is the radius. Yeah, going back, the In particular, the what is called the Gregory series, now called the Madhava-Gregory series for pi by 4 as 1 minus 1 by 3 plus 1 by 5, etc. that you know. This was derived in the Kerala tradition. And now, a lot of this study I mean the idea motivation for arriving at series expansions came from wanting to determine pi very accurately, so that they could go back and correct, they have more very refined tables for sines and so on, more correct value for the reference radius, etc. Now, the value of pi, for the value of pi you needed the series I mean the motivation was to they were motivated to find a series. Now, the series Gregory series, of course, as you know, in principle one could use it for calculating the value of pi, but it's really not workable, because to even to get a moderate accuracy you will need to add go up to a huge number of terms in the series. So, even to get 4 decimals correct, I had to add millions of terms. So, something more was needed, and there is some this is a very ingenious thing that is done. They found a correction term. If you have to truncate at the nth term and add a certain correction term, the new sequence that you get is no longer a series, but the new sequence that you get converges very rapidly to the value of pi by 4. It's a series of pi by 4. So, and that's what they used. In Sanskrit it's called the Antya Samskara is the name. They are end process, truncation process term, and with the help and there is actually it was there are more successive more and more refined versions of such truncation process, and the final one was in fact so accurate that just with about 50 terms going up to 50 terms they could get values of pi that are accurate up to the 11 decimals. Okay, so the remark to be made is that many things akin to calculus were already found in the Kerala tradition. There is a perennial debate about whether calculus started there, and which I don't want to take any sides with, about that, but the basic framework has somehow come to had set in the Kerala school. There are various questions about to what extent this influenced the developments in Europe. People have tried to find evidence to that. Though it has been rather unsuccessful. Okay. Here are some references. Brummelen, this is a nice recent book on mathematics of the heavens and the earth, which has chapters on the trigonometry both in the Babylonian, Greek, Indian and Islamic traditions. The in the Arabs also made a lot of progress in trigonometry during the corresponding period as the Siddhanta tradition in India. Then there is an article by Vibhuti Bhushan Datta and Avdesh Narayan Singh, actually revised by Krupashankar Shukla. This has appeared in the Indian Journal of History of Mathematics. Then an article of Ramasubramanian and Srinivas is also something that I would recommend strongly. Then there are many papers of R.C. Gupta on various topics on trigonometry. These are accessible from our website, which is the HTTP Indian SHM. Yeah, and two broader books to recommend. One was already mentioned as Kim Plofker by Mathematics in India, which is reviewed by Mumford, and extracts of which were read out to you. And there is also a very nice book by Saraswati Amma on geometry in ancient and medieval India. I think with some of the recent developments, it's sort of tending to get forgotten, but I think it deserves a lot more attention than it has gotten so far. So with this, thank you for your attention.
Kerala school, is it Kerala school of documentation is done in Sanskrit or in Kerala language?
No, the early works are in Sanskrit. Nilakantha, Shankaravarya, they are in Sanskrit. Jeshtadeva's, yeah, is in Malayalam. Yeah, this claim has been investigated to some extent by George Joseph and a few people, and they say they have not been successful in finding a. There's no smoking gun, is what George Joseph told me.